As we continue our discussion of the trigonometric form of a complex number, one of the things that I want to discuss is the roots of a complex number. Before I start talking about roots of a complex number, I do want to talk about this particular equation that I have here. X to the sixth is equal to 1. You might remember that as a consequence of the fundamental theorem of algebra, a polynomial equation of degree n, in this case degree 6, has n solutions. So for this particular equation, since it has a degree of 6, we should expect that over the complex number system, it's going to have 6 possible solutions. So let's try to factor this. After I set it equal to 0, I've got x to the sixth minus 1 equals 0. I can break that down into factors of x cubed minus 1 times x cubed plus 1. And that is still equal to 0. If I continue to factor this, my x cubed minus 1, using the rules of the difference of cubes, I can rewrite this as x minus 1 times the quadratic x squared plus x plus 1. The second factor, the x cubed plus 1, can be broken down into the factors x plus 1 and x squared minus x plus 1. And that is, of course, still equal to 0. If I further evaluate this, I've got solutions for x. The linear solutions here, as I take a look at this, I've got x is going to be equal to either a plus or minus 1. Using the quadratic formula, I'll determine the solutions of the two quadratics that are listed there. And the solutions for those then are as follows. I have negative 1 plus or minus I times the square root of 3 all over 2. And the second complex solution I have is 1 plus or minus I times the square root of 3 all over 2. So each of these particular solutions is a positive and negative solution. So I have 2, 4, 6 different solutions here. So I do in fact have 6 roots of the real number 1. If there's a drawback to this particular method of finding the roots of a number, the downside would be that not all polynomials represented in this way would be something that we can factor. So if we're able to factor, great, that works fine. But if that doesn't work, then we need to use what's called the nth roots of a complex number rule. I want to consider what the nth roots of 1 are, only using a method that's going to work for any value of n. For our purposes, I want to show the sixth roots of 1 again, and I want to use this other method using the roots of a complex number just to prove that it doesn't matter which method I use, both methods will give us the same answers. So right now, what I want to do is I want to take a look at the formula I have listed here. If I have the nth roots of r times the cosine of theta plus 2 pi times k divided by n, remember n is the number of roots we're looking for, plus I times sine of theta plus 2 pi k over n, that will yield us the different roots. K is going to be an integer from 0 up to n minus 1. After n minus 1, when I get to n, that is actually going to give us a duplicate root. It's going to be the same root as if I had plugged in 0 for k. So first off, if I'm going to be finding the sixth roots of 1, I want to write 1 as in a trigonometric form of a complex number. And you'll have to trust me here when I say that 1 is going to be equal to 1 times the cosine of 0 plus I sine of 0. Go ahead and figure out what those values of sine and cosine are if you so desire, and prove to yourself that that is indeed equal to 1. So by the nth root formula, remember that n is equal to 6 in this example, because we're going to try to find the sixth roots of 1. So we're going to have n is equal to 6. R is going to be equal to 1. And the rest will fill in as we go. You can see that I've substituted in 6 for n, 1 for r, and then I have substituted in 0 for theta, and 6 for n inside the cosine and sine functions as well. The next part of this, since n is equal to 6 here, I need to consider what this expression evaluates to when k is equal to 0 all the way up to and including 5. I've set up each of our expressions substituting in the values 0 through 5 for k. And I'm going to go ahead and simplify these. If I simplify the first expression there, that's equivalent to 1. The second expression is going to simplify to 1/2 plus a square root of 3 over 2 times I. The third expression is going to simplify to negative 1/2 plus a square root of 3 over 2 times I. That's where a plus or minus 1/2 plus the square root of 3 over 2 times I come from. The next one down, if I simplify that, I'm going to get negative 1. The next to last is our negative 1/2 minus the square root of 3 over 2 times I. And then the last expression that we have, that one is going to simplify down to 1/2 minus the square root of 3 over 2i. So with a little bit of rearranging here, you should be able to see that we do have the same 6 identical answers as when we had actually factored these. So this is using the complex formula for solving roots of complex numbers. In the meantime, I hope you guys have yourself a nice day. Tune in again and I'll continue the exploration of trigonometric form of a complex number with some examples.